All right, in this video, we'll begin chapter 11 dealing with introducing geometry. And with section 11-1, we're going to start that chapter with basic notations. And in this section, we'll recognize basic undefined and defined terms of geometry. Also, we'll recognize basic geometric shapes and notation associated with each shape, recognize attributes and properties of basic geometric shapes and the relationships among them, and also classify angles by their measurements. Okay, so we'll start off with some of the fundamental building blocks in geometry, which are points, lines, and planes. Some textbooks in geometry call those three words undefined terms, okay? So here we use, those are just considered to be undefined terms because we can't come up with a concrete definition of points, lines, and planes. Okay, instead of defining point, line, and plane, we describe relationships among them. Like in these two figures here we got a point A and a point B. Here's the compass. Usually with a pencil there, you have a point there. So it's usually point A. And also the needle also has a point on that compass. So that's considered to be point A. Also a safety pin with this tip at the end. That's also a point, and it's labeled point C. So usually points are labeled with a capital letter. And then a line looks like this. Okay. So if we had something like this, and then this is the center of the road, that would be a line as well. And also in a line, it looks like this. It goes on and on and on without end. And we can label this line as either a line with the word line with the lowercase letter, like line M, or since it only takes 2 points to make up a line in this case, we can label this line with those points. So it'd be line AB. Also, we can use notation for a line with two arrows going in both directions, that's line AB, or we can say line BA. The two both mean the same thing. And also the third undefined term is a plane. Usually a plane is represented as a flat surface. Okay, and it goes on and on and on without end as well. So here we can label a plane as plane ABC, or just plane with the Greek letter symbol gamma. Okay. Now, let's talk about lines first. A line has no thickness and it extends forever in two directions. Okay, as indicated, as you can see here. Extends in both directions, there is no thickness in a line. Given 2 points, there is one and only one line that connects these points. So if I have 2 points A and B, I can only have one line that goes through those points A and B. And if P and Q are any 2 points, we can create a number line on the line PQ such that there is one-to-one correspondence between the points on the line and the real numbers. Now on the next page is your linear notations here. Let's say we have this line named lowercase l. And in this case here, I have 3 points A, B, and C that are on line L, and D is not on that line. Now we're going to define collinear points, which are points that are on the same line. So in this case here, we can say that line L contains points A, B, and C. Or we can say points A, B, and C belong to line L, since those 3 points are on that line. And we can say that points A, B, and C are collinear, meaning points A B, and C are on line L. However, points A, B, and D are not collinear because notice that point D is not on the line L. Okay. That's also defined between. If you have A, B, and C, there are three distinct collinear points, then B is between A and C. If and only if AB plus AB plus BC is equal to AC. So here is an illustration of that. Of course, B in this case is between A and C. And that's because AB and BC combined together will give me AC. So point B is between points A and C on line L, and point D is not between points A and C. Reason for that is here D is not one of those distinct collinear points. Okay, next we have a subset of a line, which is called a line segment, sometimes called a closed segment. A subset of a line that contains 2 points of the line and all the points in between the 2 points is a line segment or a closed segment. So here you have endpoints A and B and all the points in between. That's a line segment. Okay, notice the difference between a line up here and the line segment. A line extends in both directions. A line segment ends at 2 points. It has endpoints A and B. The notation for that would be just a line without those arrows and then the 2 letters A, B, or we can say line segment BA. Okay. All right, next is a half open, half closed segment. Those are subsets of lines that are sometimes identified include a half open or half closed segment. And that's a segment without one endpoint. And an open segment would be a segment without its endpoints. So here's an example of a half open or a half closed segment. Here, A is not included, but B is. As you can see, the empty circle there is only at A, but a closed circle is at B. And then we have the open segment where the endpoints are not included. So here at A and at B, we have empty circles there. And these are the notations for that. Half open or half closed segment AB. And then here, this is the open segment AB. Okay. All right, next we'll look at is a ray. A subset of the line AB contains the endpoints AB. Contains the endpoints A, the point B, and all points between A and B, and all points C on a line such that B is in between A and C. Okay, so this is what a ray looks like. You only got a subset of a line. It only goes in one direction. You only have one endpoint and a point on that ray and all the points in between. Now, 2 rays are opposite rays if they have the same endpoint lie on the line segment and their union is the line. So here we got line AB. It does contain ray AB. So here we can say here that BA starts here, goes all the way to the left indefinitely. BA and also BC are considered to be opposite rays. All right, next we look at a half line. A half line looks like this. It is a ray without an endpoint. A ray without an endpoint. And a point separates a line into three parts, two half lines and the point itself. So if I have this right here, the half line BA will be denoted by an empty circle starting at B going through A, and half line BC will have the empty circle at B passing through C and point B. So here's what those half lines look like. Here at B, you have an empty circle, passes through A in this direction. Empty circle at B passes through C, the ray passes through C in that direction. Okay, statements that cannot be proven are what we call axioms. And here are a few axioms found in Euclidean geometry. In Euclidean geometry, that's named after a mathematician named Euclid. Okay, he is pretty much considered to be the father of geometry. So he's pretty much came up with things that are related to the field of geometry. And here's some axioms here. One of them, it says there is exactly one line that contains any two distinct points. There's one line that contains two distinct points. So if I was to draw an illustration of just that, it's what I mean. Okay. There's two distinct points, which I'm going to call P and Q. Doesn't matter what I call them. If I was to draw a line through them, there's only going to be that one line going through those two. And that's it. And this will be that line. P and Q, PQ. The second, if 2 points line a plane, then the line containing the points lie in that plane. Okay, so what that means here is this: if I have a plane, and this will be just an illustration of that plane, and I have 2 points, let's say M and N, they lie in that plane, then that means the line going through M and N will lie in that plane. Okay, so that means that line MN will line that plane. And in number 3, there is exactly one plane that contains any 3 distinct non-collinear points. Okay, so going back to this, if I took that plane and I have point L in that plane, that means 3 distinct points lie in that plane. And I can come up with one plane that has those 3 distinct non-collinear points. Okay. Theorems are statements that can be deduced using logic, undefined terms, axiom definitions, and previously proved theorems. In mathematics, a definition is generally stated as simply as possible with properties that can be proven omitted. Sometimes a geometric object can be defined in different ways, but all definitions must be consistent in usage. Okay. And we do have more definitions here, by the way. Starting with coplanar points. Those are points that are in the same plane. points that are in the same plane. And if you look at the next page of this handout, here is a illustration of a plane with some lines and points. Here, points D, E, and G are coplanar, meaning that points D, E, and G lie in this plane that you see here. However, we do have non-coplanar points. Those are points that cannot be placed in a single plane. So in this case here, D, E, F, and G are non-coplanar points. They're not coplanar, meaning that point F, as you can see here, is not in this plane right here that you see shaded. Okay. Next are coplanar lines. Those are lines that are in the same plane. Okay. Now in this case here, lines DE. Okay. Now I apologize for this. This should be lines DE. The D and the E should be together. D and F should be together, and FE. Those two letters should be together. Those are coplanar. Here, DE, line DE, and also line DF. Line FE. That's this line that you see here. I know it's hard to see in a two-dimensional way, but you can see here that DE lines, DE, DF, and FE are considered to be coplanar because those lines are in the same plane. Okay. And also lines DE and EG are coplanar as well. They should be DE and EG. Those are coplanar. So here's DE and EG. They're in that same plane that's shaded. So those are considered to be coplanar lines. Another definition is intersecting lines. Those are lines with exactly one point in common. So looking at this illustration, we can see that lines DE and EG, DE and G are intersecting lines. So here's DE and EG. They both intersect at a common point called E. That's the point that's common. We call that the point of intersection. Okay. Next is skew lines. Those are lines that cannot be contained in a single plane, and they are considered to be non-coplanar. Okay, so if we go back here, lines GF is GF up here, and line DE that's down here in that shaded plane. Those two lines are considered to be skew lines. Okay. And with skew lines, they do not intersect, and there is no plane that contains them. Our next definition is concurrent lines. Those are lines that intersect in a single point. So lines DE, lines EG, and line EF. Those are concurrent lines because DE, EG, and EF, those three lines intersect at a point called E. The point of intersection is point E. Okay. All right, now we got parallel lines. Those are two distinct coplanar lines with no point in common. And a line is, of course, parallel to itself. Okay. So that means here in this illustration that I have here, I have two lines, line M and line N. Line M is parallel to line N, meaning they have no points in common. And this is the notation that we use for is parallel to. So we can say that M is parallel to N. M is parallel to N. Okay. And here's some axioms about point, line, and plane. First is there is exactly one line that contains any two distinct points, which I just got through talking about not too long ago. The line has two distinct points. If 2 points line a plane, then the line containing the points line a plane. And if two distinct planes intersect, then their intersection is going to be a line. Okay. Now, I think I have an illustration of that as well. Here I got two planes, alpha and beta. They intersect at a line called line AB. Okay. Next, there's exactly one plane that contains any three distinct non-collinear points. A line and a point not on the line determines a plane. Two parallel lines determine a plane. And also two intersecting lines determine a plane. Okay. And on this next page is just some other planar notations. Here, plane alpha and beta are parallel. Those two planes don't intersect. But as I mentioned earlier with this one, if I have plane alpha intersecting plane beta, those two intersect in a line called line AB. And then next is a half plane. A half plane is a subset of a plane that consists of all points in the plane on one side of the line. Okay. So here, if I kind of let line BC or line L be a half plane, on one side of the plane would be the point D, and the other side would be something like point A in this case. So that's basically what a half plane is and what it looks like. Okay. So now we're going to take some of this and look at some of the examples here that are related to points, lines, planes, and some of the other definitions that we have here. All right, let's look at example 1. The figure below is a rectangular box in which EF, GH, and ABCD are rectangles, and line segment BF is perpendicular to planes EF, GH, and ABCD. Use the figure to complete parts A through E. Okay, so now we're going to look at each one of these one at a time, starting with part A. In this case here, we want to name one pair of skew lines. And that means I want to identify the lines, a pair of lines where they're not in the same plane and they do not intersect. Okay. And usually in a problem like that, they would pretty much give you a choice of answers. Okay, so like in this one, part A, they do give you a choice of answers, which pair are skew lines. Okay, let's try A, B, and C, D. Here's A, B up here, and here's CD right here. Those are not skew lines because A, B, and CD are in the same plane. What about EH and FH? Here's EH down here, and FH is right here. Those two lines do intersect at a point. It may be hard to see, but EH and FH do intersect at a point. Well, what about line segment AB up here and EH, which is down here? That would be a pair of skew lines because AB is in one plane, EH is in another plane. Okay, so AB and EH would be a pair of skew lines. So I'm going to go ahead and write this as line segment AB and line segment EH. Okay. All right, so that's part A. Now part B, what is the intersection of the planes EFG and AEF? What is the intersection of planes EFG and AEF? Well, here's EFG. That's this plane at the bottom. And AEF would be AEF. That's this plane on the far left here. I know that's hard to see, but there they are, ABF and EFG. Well, if I look at it, the line of intersection, two planes intersect in a line, so it has to be line EF. Has to be line EF. Okay, and maybe if I show this in colors, this might help. EFG is down here. That's that plane. And then AEF is AEF. And an intersection line, EF. Okay. Part C, plane, EAB. EAB is this one on the far left. Is perpendicular to what? Okay. And in this case here, the choice of answers is right here. So here they're giving you a drop-down menu in the homework. So pretty much you'll just have to determine which one fits, which one of these will fit the fact that EAB is perpendicular to what? So EAB is perpendicular to, let's see. In this case here, would it be perpendicular to AB? But here's AB right here. That would not be it. What about plane DCG? Let's see, DCG is way over here. EAB is over here somewhere. Those two are not going to be perpendicular. And what about FG? This is FG right here. Notice that box right there. It shows that these two form a right angle. And anything that forms a right angle means that it's going to be perpendicular. So that means that FG, line segment FG, will be perpendicular to EAB. And part D, what is the intersection of line segment BC and plane EFH? Let's see, EFH is down here. And BC is up here. Okay. And here's the choice of answers that they're giving you. It's going to have to be the empty set. because notice here, EAB, here's EAB on this side, and BC is up here. Okay, those are in two different planes, by the way, and those are skew. Okay, so that means it's going to be the empty set. Oh, I'm sorry. EFH is down here. EFH is down here, and BC is way up here. Those are in two totally different planes, so the empty set would be the correct choice. And part E, explain why planes EAD is EAD, that's this plane in front, and DCG, that's this plane off to the side, are perpendicular. Okay. And in this case here, they do give you the choice of answers here to choose from. Okay, explain why planes EAD and DCG are perpendicular. And the reason for that would be this, it's this. The intersection of the planes is a single line, and the planes form a right dihedral angle. So that would be answer B. All right, so for a homework problem like this, you'll be given a choice of answers, and then you just have to pick which one would best fit that description or fit the question. Okay. So that's homework example number 1. All right, now homework example number 2, we're going to be using a pyramid to complete parts A through F below. In this case, now I just, in the handout, I just copy and paste the questions, but in the homework, it's going to look like this. With choices of answers, you just pick and choose which one will fit that situation, like in part A. What is the intersection of AB and AD? Line segment AB and line segment AD, that's right here. Well, in that case, that's just going to be point A. So you'll choose point A as the answer. I'm just writing in point A. All right, and then part B. What is the intersection of planes ABE, BCE, and ABC? So we got ABE, that's going to be this face in the front. Then BCE, that's this space over here. And then ABC, which is this base down here at the bottom. We want to find the common intersection of those two. And by looking at this, with these answer choices that they give you, that's just going to be point B, okay? And by the way, if you look at it, ABE, then BCE, and ABC, B is included in all three of those. So it must be point B. That's the intersection of those three planes, ABE, BCE, and ABC. All right, part C, what is the intersection of AB and BC? Well, here's your choices right here. And by looking at this, it will have to be point B. Reason B, here's line, segment, line AB. I can show you right here. Here's line AB and line BC. The point of intersection is at B, so it must be point B. Part D, which pair of lines are skew lines? And here are the answer choices for that. Skew lines are lines that are in a in two totally different planes and do not intersect. Okay, so if I look at AB and CD, here's AB, here's CD. They're both in the same plane. They don't intersect, but they're in the same plane. For it to be skew, they cannot be in the same plane. What about DE and CE? Here's DE up here. CE is right there. They're both in the same plane. And they do intersect at a point, which is point E. Okay. What about AB and DE? Here's AB. DE is up here. DE is in a different plane than AB, and they don't intersect. So I can say, well, take that back. AB and DE. Those do intersect at D. Well, this is in a plane that intersects, so that's not going to work. So well, I was right, AD and DE. Those are in the same, those are in two totally different planes and they don't intersect. So in this case here, line segment AB and DE, or lines AB and DE. Now part E is to find a pair of distinct parallel lines. So here we're going to choose what our parallel lines are from that. Well, let's see, AD and BC. Well, take that back. With this, if I look at AB and BC, those intersect at a point. But what about AB and DE? AB and DE, those are actually skew lines that we just got through talking about. What about AD and BC? Here's AD over here, BC is over here. Those are a pair of parallel lines. They're in the same plane, but they do not intersect. So AD and BC are a pair of distinct parallel lines. So AD and BC. AD and BC, same plane, they don't intersect. So those are two distinct parallel lines. All right, in part F, on a plane not determined by one of the triangular faces or by the base. What about this one, AEC? Okay, AEC. And of course, you are given a choice of answers here. Okay, so in this case here, if you look at AEC, you'll see that it's not formed. It's not one of the triangular faces. Because if you check the others, they would be like BAD. Here's BAD, that is a base. The other one was AEB. That's one of the triangular faces. And CED is another one of those triangular faces. That's this triangle face on the back. But AEC is not. So with homework example number 2 in my math lab, they do give you a choice of answers to a select. Okay, so that way you won't have to think and figure it out or enter an answer in, but you'll just have to pick and choose. Okay, now let's go to angles here. An angle is formed by two rays with the same endpoint. So here's an example of what an angle looks like. We have two rays with the common endpoint, and that common endpoint is called the vertex. Okay, and the sides of the angle, those are the two rays that form that angle. So ray AB is one side and ray BC is the other side. And the common vertex, which is the common point, which is point B, that's your vertex. And we can label an angle in one of three ways. We can label it by the vertex itself, which is going to be angle B, and that's the notation for angle. And then angle ABC, where the vertex, if you use three letters, the letter in the middle will be your vertex. Or we can say angle 1. Sometimes angles are labeled by numbers. Okay. All right, so that's what an angle is and what it looks like. All right, now for the interior of an angle, whose sides do not lie in a straight line, is the region in the plane encompassed by the two sides of the angle. The interior of angle ABC is the set of all points in the intersection of the half plane determined by line BC and point A, and the half plane determined by line AB and point C. Okay, so in this case here, this is the example of what an angle looks like. Here's angle ABC, or you can call it just simply angle B by just the vertex itself. The space that's on the inside of those two rays represent the interior of angle ABC. Now keep in mind that points A, B, and C are not in the interior of angle ABC. Those are points that are on those two, on that angle. They're not on the inside. All right, next we'll look at adjacent angles. Those are two angles with a common vertex on the common side, but without overlapping interiors. So in this case here, let's say we had this illustration here, angle QPR is adjacent to angle RPS, as you can see here. Those are angles that are next to each other. They have a common side, which is going to be ray PR. And the common vertex, of course, is B. So we can say, if we were to label these with numbers or with Greek letters, like in this case here, alpha and beta, those are considered to be adjacent angles. Okay. All right, next is angle measurement. An angle is measured by the amount of opening between its sides. The degree is commonly used to measure angles. A complete rotation about a point has a measure of 360 degrees. And we can write that with 360 with a small degree sign to represent 360 degrees. 1 degree is 1 over 360 of a complete rotation, or 1/360th of a complete rotation. The measuring devices used to measure angles is a protractor. So here's just an illustration of what a protractor is, what it looks like. It goes from 0 all the way up to 180 degrees. And by the way, when you make one complete rotation from here all the way to the end, that complete rotation has a measure of 360 degrees. Okay. On the next page, a degree is subdivided into 60 equal parts or minutes, and each minute is further divided into 60 equal parts or seconds. So here, 1 degree is equivalent to 1/360th of a rotation about a point. And 1 minute is going to be 1/60th of a degree. And 1 second is 1/60th of a minute. Okay. And if you were going straight from degrees to seconds, what you could do here is take 1 degree, multiply it by 1/60th, and then times 1/60th again. Now we're going to look at some examples of how to convert to degrees, minutes, and seconds. Like in this example here, let's convert 8.42 degrees to degrees, minutes, and seconds. Okay. So in this case here, I'm going to take that 8.42. Let's start with minutes, okay? Because I know 1 degree is 60 minutes. Okay. Now, this is what I'm going to do here. I know I have the 8. That's 8 degrees right there. And then that 0.42, since it takes 60 minutes to make up 1 degree, I'm going to multiply the 0.42 by 60. Okay, so using the calculator, 0.42 times 60 would give me 25.2. So this is 8 degrees, and then I got 25.2 minutes. And this is the symbol for minutes, by the way. That's the symbol for minutes. And for seconds, it's this symbol right here. That's going to be the symbol for seconds. Okay. But my minutes and seconds have to be whole numbers here. The minutes, I have 25.2 minutes. Let's convert that part into seconds. So I have 8 degrees with the 25 minutes. That 0.2, that's the decimal part. I need to convert that to seconds. Well, 1 minute is 60 seconds, so I'm going to multiply 0.2 by 60. That would give me 12. So I'm going to bring this down. 0.2 times 60 would be 12, and that would be 12 seconds. So the way I'm going to write that in degrees, minutes, and seconds would be this: 8 degrees, 25 minutes, 12 seconds. That's how I convert that from degrees, minutes, and seconds. Okay. Now for this one, let's say I want to convert 47 minutes, 47 degrees, 45 minutes, 36 seconds as a number of degrees. So here I got 47 minutes, 45 degrees, 36 seconds. Let's start with the converting 36 degrees into a decimal part in seconds. 36 seconds into a decimal part in degrees. So this is what I'm going to do. I'm going to take the 36, multiply that by, well, a second is 1/60th of a minute. So that'd be multiplied by 1/60. or take 36 and divide that by 60, by the way. So I'm going to bring down the 47 degrees, 45 minutes plus, and this is going to be in the form of a minute. So 36 divided by 60 would be 0.6. So this is actually 0.6 minutes. Now add that to the 45 minutes, you're going to get 47 degrees plus 45.6 minutes. Now I'm going to go from minutes to degrees. Well, the minute is 1/60th of a degree. So let's do this. Bringing down the 47 degrees, and then 45.6 would be multiplied by 1/60th of a degree. So actually I can do 45.6 divided by 60. I'm going to get 0.76 as the answer. So this will be 47 degrees plus 0.76 degrees. Now I can add these two together. I'll end up with 47.76 degrees. Okay. So 47 degrees, 45 minutes, 36 seconds, expressed as a number of degrees would be approximately 47.76 degrees. Okay. All right, here's another example. Let's say I want to find the measure of angle BAC. If the measure of angle 1 is equal to 47 degrees, 45 minutes, and the measure of angle 2 is equal to 29 degrees, 58 minutes. Okay, so we're finding the measure of angle BAC. Here's B, that's A, and that's C. That's this angle measured that I'm trying to find. And I already know what the measure of angle 1 is. That's this whole angle right there, 47 degrees, 45 minutes. The measure of angle 2, that's this angle part right there. That's 29 degrees, 58 minutes. In this case, I'm going to have to do a little subtraction. Subtract this angle minus that angle will give me the angle that I have marked in green. Excuse me. All right. This is in minutes here and here. Now, I cannot subtract 58 minutes from 45 minutes. Okay, I need to do a little regrouping here. I need to take away 1 degree from 47 degrees. That will leave me with 46 degrees. Okay. Now that 1 degree that I took away, I'm going to convert that to minutes. 1 degree is 60 minutes. So if I add the 60 minutes to the 45 minutes, I will end up with 105 minutes. And then I can subtract 29 degrees and 58 minutes from that. Well, if I subtract 58 from 105, that will be 47. So it'll be 47 minutes here. 29 from 46 will be 17 degrees. Okay, so the measure of angle BAC, that's this angle here, will be 17 degrees, 47 minutes. Okay. All right, now let's look at some homework examples that deal with the protractor. Okay. And in this case, I want to use the protractor to find the measure of each angle, like the measure of angle CAD. Let's see, here's C, this is A, and that's D. CAD, that should be easy to read. We just read across where this ray is crossing the protractor. And in this case, it's crossing the protractor right there at 60 degrees. At C is 0. From 0 to here, that's 60 degrees. So the measure of angle CAD, sometimes we like to write like this, the measure of angle CAD is 60 degrees. Then part B is the measure of angle EAB. Measure of angle EAB. Let's see here. Here's E up here. There's A and that's B. Let's look at where these rays are crossing on this protractor. Since it's not positioned at 0, we're going to find out where these rays are crossing the protractor, and then we subtract. At AE, that's this ray right here, is crossing at 90 degrees. And at AB, that ray is crossing the protractor at 20 degrees. Okay. So if I do 90 degrees minus 20 degrees, that's going to give me 70 degrees. So in this case here, the measure of angle EAB is going to be 70 degrees. Okay. Now for the measure, part C, the measure of angle DAB. Let's see. Here's D right here. AD, that ray is crossing that protractor at 60 degrees. And then we have to subtract from it where the ray is where AB is crossing the protractor at 20 degrees. So 60 degrees minus 20 degrees is 40 degrees. So the measure of angle DAB will be 40 degrees. And then finally, the measure of angle HAD. Let's see, A is here, there's H right, way over here. It's at 180 degrees. All right, but for AD, that's right here. It's crossing the protractor at 60 degrees. So 180 minus 60 ends up being 120 degrees. So the measure of angle HAD is 120 degrees. Okay. All right, here's another homework example. All right, we're going to complete parts A and B here in this case, perform each of the following operations. So in part A, part 1 of A, we got 11 degrees, 45 minutes, 30 seconds, plus 14 degrees, 46 minutes, 37 seconds. And here we just add the two together, but we have to keep in mind that for every 60 seconds, it's 1 degree, and 1 minute, and for every 60 minutes is equal to 1 degree. So if I add 30 and 37 together, that would be 67 minutes, 67 seconds. 45 minutes and 46 minutes would be 91 minutes. 11 degrees and 14 degrees is 25 degrees. But we need to simplify this. Well, for every 60 seconds, that's equivalent to 1 minute. So if I subtract 60 seconds from the 67 and add 1 minute to 91 minutes, this is what I'll have. 25 degrees, 92 minutes, 60 from 67 would be 7 minutes. Okay. 92 minutes, 7 seconds. Okay, but for the 92 minutes, 60 minutes make up 1 degree. So I need to subtract 60 from the 92, 60 minutes from 92, and add 1 degree to the 25 degrees. So now this will be 26 degrees. 60 from 92 will be 32 minutes, 7 seconds. Okay, so that will be the final answer in simplest form. 26 degrees, 32 minutes, 7 seconds. Part 2 is subtracting 16 degrees, 21 minutes minus 5 degrees, 53 minutes. Well, I can't subtract 53 minutes from 21 minutes. So what I need to do here is take away 1 minute, 1 degree from 16. That'll leave me with 15 degrees. And then that 1 degree gives me 60 minutes. So I add 60 minutes to the 21 minutes, that'll be 81 minutes. And now we can do the subtraction. 53 degrees, well, 53 minutes from 81 minutes will be 28 minutes. And then 5 degrees from the 15 degrees will be 10 degrees. So the final answer there will be 10 degrees, 28 minutes. All right, now part B is to express the following without decimals here. Here we got 0.8 degrees. And we're going to do this in degrees, minutes, and seconds. So here, there are 60 minutes in 1 degree. So I'm going to take the 0.8 multiplied by 60 minutes. So the 8 times 0.60, or 0.8 times 60, 0.8 times 60. That would be 48. So the answer there would just simply be 48 minutes. So 0.8 degrees converts to 48 minutes. And that's as far as we'll go with that problem. And that's part 1. Now part 2 is 17.31 degrees. We want to convert that into degrees, minutes, and seconds. All right, so we have the 17 plus that 0.31. I need to convert that to minutes by multiplying it by 60. So this will be 17 degrees here. 0.31 times 60 would be 18.6. That's 18.6 minutes. So now I need to convert that because I want the minutes to be a whole number. So bring down 17 degrees plus that 18.6. I'm going to convert that to seconds. Well, actually, the 18 would be the minutes. It's the decimal point I want to write in terms of seconds. 18 minutes plus, and then 0.6. I'm going to convert that to seconds by multiplying by 60 seconds. So 0.6 times 60 would be 36. So I have 17 minutes with the 17 degrees with the 18 minutes, and this time plus 36 seconds. So my final answer there will be 17 degrees, 18 minutes, 36 seconds. 17 degrees, 18 minutes, 36 seconds. All right, now let's look at the types of angles here. There are 4 types. One of them is an acute angle, where the measure is less than 90 degrees. Between 0 but less than 90 degrees is an acute angle. A right angle is going to be an angle with a measure of exactly 90 degrees. So this is a right angle here in this case. And usually a right angle will be indicated by a box at the vertex of that angle to indicate you have a right angle, which is exactly 90 degrees. An obtuse angle is an angle that is more than 90, but less than 180. Okay, so angle AOB in this case would be an obtuse angle. And then finally, a straight angle is an angle with a measure of exactly 180 degrees. Okay. Now, a straight angle can be described without referring to degree measures. A straight angle is an angle whose sides are opposite rays, forming a straight line. Okay. All right. Now let's look at circles and arcs. Circles and arcs. A circle is a set of all points in a plane that are the same distance or the radius from a given point, called the center. Okay. So here's an example of what a circle looks like on the left side here at the bottom. Okay, you do have a point in the middle that's called the center. Okay, now, when we talk about the radius, we're talking about a line segment that connects from the center of the circle to a point on the circle. That is considered to be a radius in this case. An arc is any point on the circle that can be drawn without lifting the pencil. So if I have 2 points C and D, the distance between those 2 points, that's called the arc. We can call that arc CD or use this symbol to represent arc CD. And a chord is going to be any segment with endpoints on the circle. So with this illustration here, line segment BC, you can see here, that is considered to be a chord, because it's a segment with endpoints on the circle. And a chord that contains the center of the circle, like this one, we call that the diameter, okay? Because it has the 2 endpoints on the circle, the segment goes through the diameter. Goes from one point on the circle through the diameter to another point on the circle. And by the way, there are some relationships with the radius and the diameter. In this case here, your diameter, the length of the diameter will be twice the length of the radius. Also, your radius will be, the length of the radius is considered to be half the length of the diameter. And also in circles, you have what they call central angles and central arcs. A minor arc is one determined by a central angle whose measure is less than 180 degrees, while a major arc is determined by a reflex angle whose measure is greater than 180 degrees. Depending upon the context, a central angle and its associated arc have the same degree measure. An arc is determined by a diameter. An arc determined by a diameter is called a semicircle. A semicircle of circle O in the figure also is considered to have center O. So let's look at what we're talking about here. The minor arc in this case would be something like this. AB, arc AB is a minor arc. Whereas ACB, here's A, C to B. Let's call it a major arc. A, C, then all the way around to B. That is a major arc, okay? Because the measure is going to be greater than 180 degrees. And also, arc AD, as you can see here, that's considered to be the semicircle. And it is considered to have the center called O. Okay, so let's look at this example here dealing with central angles and arcs. In this case here, we're given the figure below and we want to find the following. Like in part A, I want to find the measure of arc AB associated with the central angle AOB. In this case here, let's see, here's A, here's O, and that's B. Now there's something that you do need to know here. I know something about this 60-degree angle here, along with this angle that I'm trying to find. I know those two form a straight angle. And in a straight angle, its measure is 180 degrees. So if I subtract 60 from 180, this will be 120 degrees. And also, I know this. If this angle is 120 degrees, then the measure of this arc, AB, has to be the same as the measure of this central angle here. So if this is 120, then arc AB must be equal to 120 degrees. Okay. Now in part B, we want to find the measure of arc AF. This is AF over here on the left side, associated with the central angle AOF. Here's A, here's O, and there's F. Well, angle AOF, that central angle is 60 degrees. So that means that arc AF will have the same angle measure as angle AOF, which means that the measure of arc AF is 60 degrees as well. Part C, finding the measure of arc BC, that's here, arc BC, associated with the central angle BOC. BOC is right here, B, O, and C. Well, I've already found out that the measure of angle AOF, AOB, which is the central angle, that's 120. And these two form a straight line. That's 180 total. So if I subtract 120 from 180, that will mean that this angle has a measure of 60 degrees. And if this central angle BOC has a measure of 60 degrees, then arc BC has that same angle measure. Arc BC has the same angle measure, which is also 60 degrees. and then find the measure of arc FDC. This is FDC. I'm going to do this in green. Arc FDC, that's that. And it's associated with the central angle FOC. And here's FOC right here. Well, that's 60. These two form a straight angle. So if I subtract 60 from 180, that's going to be 120. And this angle, this length here, or the measure of that arc, has to have the same as the angle measure, the central angle measure. So if this is 120, then arc FOC is also going to be 120 degrees. Okay. All right, so that's how we do that example there. Okay. Now let's look at homework example number 5. In the figure below, A is parallel to B, and O is the center of the circle. A is parallel to B, and O is the center of the circle. So in this case here, I want to find the following measures here. Let's say the measure of arc BC. Here's BC right here. And I know this central angle here has a measure of 58 degrees, as you can see. That means that the measure of the arc has to have the same as the measure of the central angle. So central angle BOC is 58, then that means that arc BC must be 58 degrees. Okay. Now, arc B. And in this case here, the measure of arc CD. Measure of arc CD, that's this right here. Let's look at that central angle right there. That's 122 degrees. So here, the measure of this arc has to be the same as the measure of the central angle. So if that's 122, then arc CD has a measure of 122 degrees. Now part C, the measure of arc AD. Well, let's see, AD is right here. And that angle measure there is 58 degrees. So that means arc AD must also be 58 degrees. And then the measure of arc AB, that's part D. Here's AB up here. Well, that angle measure, let's see, the central angle measures AOB. That's 122. So the arc measure, the length, the measure of that arc has to be the same as the central angle measure. So if that's 122, then arc AB must also be 122. And finally, part E, the measure of arc DCB. Let's see, DCB, this is all the way around here. Here's D, that's C, and that's B. Notice, this whole thing is a semicircle. DCB is a semicircle. And I need to include 122 degrees and 58 degrees. That's going to be a total of 180 degrees. So that means that the measure of our DCB must be 180 degrees. Okay. All right. Now let's look at homework example number 6. Describe the size of angles of the pieces of a circular pizza if the pizza is cut into equal size slices in the following number of pieces. Starting with part A, which is 4. Now let's think about this, a circular pizza. We're going all the way around, and we want to find the angle measure of a circular pizza. Well, for all circles, the angle measure has to be 360. If you start from one end, go all the way around and come back, that's 360 degrees. And we cut that into 4 equal slices. So if I do 360 divided by 4, (360 divided by 4), that should give you 90 degrees. So the size of the angles of the pieces of a circular pizza would be 90 degree slices. Okay. And now part B, 8. We want the pizza cut in 8 equal slices. So that's 360 divided by 8. That will be 45 degrees. And then part C, 20 slices, 20 equal slices. So 360 divided by 20. That's going to be what, 18 degrees? So each slice will have an angle measure of 18 degrees. And part D, n slices. Well, in general, that would be 360 divided by n. Okay. And that would be as far as we can go with that problem. Okay. So you have to think of the fact that a circular pizza has an angle measure of 360 degrees. You'll just divide each of these into 360 to get your answer. All right, next page, we'll deal with perpendicular lines. All right, perpendicular lines are lines that intersect at 90-degree angles or a right angle. So in this case here, I got 2 lines, line M and line N. Line M is perpendicular to line N. And here they use the box to indicate that these 2 lines form a 90-degree angle. And this is the notation. M is perpendicular to N, or we can use the points on that line and say line AB is perpendicular to line BC. Actually, line segment AB is perpendicular to line segment BC. Or line segment BA is perpendicular to line segment BC, or line segment AB is perpendicular to line segment BC. And I think we're saying the same thing here. Okay, what about a line perpendicular to a plane? A line perpendicular to a plane that is perpendicular to is a line that is perpendicular to every line in the plane through its intersection with that plane. So here, let's say we have a plane alpha. And let's say that there's a line perpendicular to it. Then every line in that plane will be perpendicular to every line in the plane through its intersection with the plane. So here we've got two planes that are perpendicular. Okay. So every line, so the line that's perpendicular, this line right here, BA, will be perpendicular to every line in that plane through its intersection. Okay, got two more things to cover, and I'll be done. One would be the perpendicular planes. If P is a point on any plane, if P is a point on line segment AD, Q is in plane alpha and S is in plane beta, so that PQ, here's PQ right here, is perpendicular to AD. Here's AD. And also PS is going to be perpendicular to AD. Then that means that angle QPS will be a right triangle. And since angle QPS measures 90, that means that these two planes, alpha and beta, will be perpendicular. Okay, so here you have two perpendicular planes here. And then this last thing we'll talk about is the dihedral angle that is formed by the union of two half planes and the common line defining the half planes. So here, dihedral angle is measured by any of the associated planar angles, such as angle OPD, which is this angle right here that I'm showing, where PO, line segment PO, is perpendicular to AC, and PD, line segment PD, is perpendicular to line segment AC. Okay. Okay. So that's what a dihedral angle looks like. Okay. As we got two half planes, alpha and beta, and the common line, which is going to be line AC, and it defines the half planes. Okay, so that will conclude this ever so lengthy video on section 11-1 dealing with basic notations. Feel free to email me or contact me if you have any questions about anything presented in this video, or if you have any issues with the homework in my math lab.